Hi everyone, welcome to my talk. I am Zhen Xie, a postdoctor in University of California, Merced. In this talk, I will present a paper, Tahoe, Tree Structure-Aware High-Performance Inference Engine for Decentralized Ensemble on GPU. This is a joint work with my fellow student and my advisor, Professor Dong Li. Okay, so what's the tree inference? Decentralized is a highly effective structure within which you can lay out options and investigate the possible outcomes of choosing those options. Decentralized inference can be used to help build automated and predictive models. As we can see from this figure, this tree has one root node and multiple decision node and leaf node, which can be used to determine whether I accept this job or not. It includes salary, commute hour, and free coffee. These things are helpful for us. So, how is the decentralized inference actually used? A lot of companies use GPU for tree inference to leverage massive thread-level parallelism and high memory bandwidth to provide high-throughput inference. For example, Facebook uses high-throughput tree inference engine on GPU to decide which notification to send to billions of users, as well as Microsoft uses select customized content to display. NVIDIA uses a high-throughput tree library, Rapids FIL, on GPU to serve massive inference requests. However, to enable high-throughput inference on GPU has some performance bottlenecks. The first one is different GPU threads traverse different trees and can take different tree passes and access different attributes of input samples during the forest traverse, which causes irregular memory access patterns and node imbalance problems. The second one is given a sample for inference. Each thread uses its assigned trees to make a prediction, and then one thread performs a thread reduction to compute the final prediction. It also has high overhead. So, we started this problem using a random forest trained by XGBoost on a common dataset, Hedges. For the first figure, we observe that the ratio of requested data to total data fetched from global memory is only 16.7% because of uncorrelated memory accesses. From the second figure, the reduction operation takes up to 53% of total inference time in our example with 120 trees. This figure shows the execution time of thread in a thread block. The thread block performs inference for 1000 samples. We use coefficient of variation to quantify the variance. CV equals to almost 50%, indicating a large variance in execution time across threads. So, to solve these performance bottlenecks, this paper proposed Tahoe, a tree structure-aware high-performance inference engine on GPU. Tahoe designs an adaptive forest format to enable correlated memory accesses and node balance. Besides, we introduce a set of inference structure, each of which use shared memory differently and has different implications on reduction overhead. We also introduce performance models to guide the selection of inference structures. Then, we will introduce them in details. Adaptive forest format introduces two techniques to rearrange nodes and trees. The first one is probability-based node rearrangement. Based on the information of edge probability, if the left child has lower probability to be visited than the right child, we swap the two children nodes. The method goes from top to bottom of the tree. For this figure, the edge probability of two children nodes of the root node at the second level is 0.3 and 0.7. The right children node has high probability to be visited than the left child node. Hence, two children nodes are swapped. The second one is similarity-based tree arrangement. We address the node imbalance problems based on the similarity of trees. We claim two trees are similar if during inference the two trees tend to be traversed using the similar paths and accessing similar attributes. As we can see from this figure, the order of trees lined in memory is T2, T3, and T1 because T2 and T3 has the largest similarity and T3 and T1 has the second largest similarity. Then we study how to address the problems of high reduction overhead. We also explore how to make best use of shared memory for high performance. To avoid the reduction and explore performance potential of shared memory, we introduce several inference strategies as follows. These strategies use the shared memory and the reduction mechanism differently. We study the performance of the four inference strategies using 50 datasets on NVIDIA 100 GPU. The result is shown in this figure. The red marks are the method that corresponds to the best performance. For example, direct method performs better than others in two datasets, SVHN and GIST. The Shine Forest method performs better than other strategies in 5 datasets. We can easily observe that no single structure can perform best in all datasets. Motivated by the insights, we use performance modeling to decide which inference structure should be used for best performance. The detailed performance models are listed below, and you can get more explanation from our paper. Besides, the performance modeling is used only once at each batch. It is also highly lightweight and only takes up to 3% of an inference time. We evaluated this work using a high-end server with 3 generations of GPUs, including Tesla K18, Tesla P100, and Tesla V100. The input data includes 50 datasets from UCI and libsvm, in which 70% of each dataset is used for training and 30% is used for inference. The baseline we used is a high-throughput tree library (FIL) in NVIDIA Rapid Suite, which is a state-of-the-art and open-source library. This figure shows the throughput on all datasets. We choose performance of using 2 batch sizes, 100,000 representing the use cases with highest parallelism, and 100 representing the use cases with no parallelism. It shows that Tahoe performs much better than FIL. For the high parallelism task, Tahoe introduces over 3 times speed up on average on 3 generations of GPUs compared to FIL baseline. For the no parallelism tasks, Tahoe introduces over 1.4 times speedups on average on the 3 generations of GPUs. We use NV proof to quantify the load efficiency of shared memory and global memory when accessing forests. With Tahoe, the global memory rate throughput is improved greatly on 3 GPUs. We merge the average coefficient of variation of execution time across threads in a thread block in the 50 forests. The average coefficient of variation is reduced by over 60% on 3 generations of GPUs. In particular, the biggest forests gain the largest benefit from load balance because there is a large variance in these forests. Tahoe also removes block-wise reduction for 27 cases from 45 cases. In conclusion, we reveal 3 common performance problems in decentralized inferences. We introduce Tahoe, an inference engine on GPU that considers the common paths of tree traversal and the similarity of tree topologies to address these problems. Tahoe largely outperforms an industry-quality inference engine. I'm done with this talk. Thanks everyone. I'm ready to take any questions.